Dear friends, in Ravi Chhatri here would like to welcome you to learn statistics. Watching videos of the lecture series related to teaching learning activities in mathematics and statistics. In the previous videos, we discussed binomial, normal and inverse normal distributions. Today in this video, I would like to discuss how to approximate binomial distribution using normal distribution.
We know that the binomial distribution is the probability distribution of a discrete random variable in which the probabilities are distributed at the discrete points, whereas the normal distribution is the probability distribution of a continuous random variable where the probabilities are defined under the smooth curve in a range or in an interval. These figures represent an experiment of tossing 10 coins with binomial parameter n is equal to 10 and p is equal to 0.5. The corresponding normal parameters are mu is equal to 5 and sigma is equal to 1.58. If the binomial parameter n, the number of trials, gets larger and larger, especially greater than 30 in a binomial distribution, then computing binomial probabilities becomes a complicated task. Also, as n gets larger and the parameter p, the probability of success becomes smaller, it is better to approximate this binomial distribution with a normal distribution. But first, make sure that these binomial conditions are met for this approximation. Before going to the actual problem of approximating this binomial distribution with this normal distribution, let's try to visualize the scenario by considering a random experiment of tossing 50 coins and see how the probabilities differ in these two distributions, binomial and normal. Here, the outcome of these experiments are heads or tails. Let's define a random variable x that counts the number of heads in this experiment. With reference to this experiment, in the binomial distribution, parameters are n is equal to 50 and p is equal to 0.5, and the events are discrete here. Whereas in this normal distribution, the parameters changes to mean mu equal to 25 and the standard deviation sigma equals 3.54. And the events are continuous here in a range or in an interval. In the binomial distribution, we consider these point probabilities p x equals k at the discrete points, which ranges from 0 to 50. And the cumulative probability, like probability random variable x less or equal to k, adds all these point probabilities from 0 to k. The equivalence of these probabilities in normal distribution are the measure of the areas under the smooth curve within the respective intervals. For example, the binomial point probabilities px equals k are approximated by the measure of the area under the smooth curve within the intervals k minus 0.5 to k plus 0.5. And in probability notation, it is expressed as p k minus 0.5 less than equal to x less than equal to k plus 0.5. Similarly, the cumulative probability x less than equal to k in normal distribution measures the area under the smooth curve within the interval that ranges from negative infinity to k. The objective of the present discussion is to convert the discrete events shown in this figure into the continuous events that can be defined in this smooth normal curve. This conversion process is the normal approximation of the binomial distribution. Now let's start the step of this approximation process. In the first step, we need to check these binomial conditions, whether the product of the number of trials and probabilities are greater than or equal to 5. In the next step, we shall change the binomial parameters NP into normal parameters mu and sigma using this relationship. The last step is the continuity correction. That is, we need to change the binomial discrete events into the normal continuous events. Consider the discrete event x is equal to 6. That is, the random variable x taking a point value 6. The probability of this event x is equal to 6 equals 0.2, corresponding to this value here. That is, in the discrete probability space, the discrete point value has some non-negative probability. Let's consider the same event x is equal to 6 in the normal distribution, a continuous probability space, and try to find the probability of this event, probability x is equal to 6. Here, the probabilities are measured in terms of area. The event x is equal to 6 is a line whose area measure is 0. That is, probability x is equal to 6 is equal to 0. Hence, the point probabilities in continuous probability space, such as in normal distribution, are 0. So, our task here is to change such discrete event into equivalent continuous events using the process of continuity correction. To proceed further, let's discuss some rules that applies in converting discrete events into continuous events. Now let's discuss the rules of converting discrete events in the binomial distribution into the continuous event in the normal distribution. Let the value of k be 25. That is, we shall look the probability events at 25 or near to it. First, the point probability at x is equal to 25 in the binomial distribution is approximated by the measure of area under the smooth normal curve within the open interval that ranges from 24.5 to 25.5. Now let's discuss the left cumulative probabilities. Probability x less than 25 is approximated by the area under the normal curve within the right closed interval from negative infinity to 24.5. Next event, the probability x less than or equal to 25 is approximated by the area under the normal curve within the right closed interval that ranges from negative infinity to 25.5. Next, we shall discuss the right cumulative probabilities. The first probability x greater than 25 is approximated by the area under the normal curve within the left closed interval that ranges from 25.5 to infinity. The last event, the probability x greater or equal to 25 is approximated by the area under the normal curve within the right closed interval that ranges from 24.5 to infinity. Let's discuss with examples the different scenario that we may come across in the process of approximation. First, the approximation of discrete point into a continuous interval. Consider this example of 85 students out of 200 need to take math prerequisite course. In the past, 40% of them took this course. The parameters here are n is equal to 200 and the probability p is equal to 0.4. The point value of the random variable x equals 85. So the question here is to approximate binomial discrete probability x equal to 85 into normal continuous probability. Here in this figure, the point probability at x equals 85 is shown by a vertical line of height 0.044 that measures the discrete probability. Equivalently, in this normal distribution figure, the point 85 is changed to an interval that ranges from 84.5 to 85.5. The probability measure is the area included in the interval below the smooth curve. Below each figure, the R solution is given. If we copy this command and paste at the R console, we get the probability of the discrete event. Similarly, if we copy this command and paste at the R console, we get the result probability of the continuous event. Here we see that the result matches up to the third places of decimal. Next, we shall discuss how the binomial discrete cumulative probabilities are approximated by the normal distribution. As we have already discussed the rules of approximation, the open discrete probability for this lower tail event that the random variable x taking values is strictly below some specified value x is approximated by the area in an interval ranging from minus infinity to 0.5 less than the value x in the normal distribution. Consider this example of placement test. Here we are interested in finding the probability in which fewer than 28 out of 200 students will not pass the placement test. In the past, 20% didn't pass the test. Here, binomial parameters are n is equal to 200 and p is equal to 0.2. Here in this problem, we are approximating the discrete probability that the random variable x strictly lies below 28. In probability notation, we write this as this expression. Since x is strictly less than 28, here in this binomial figure, the computed sum of the discrete probability from negative infinity to 27 is shown here. Equivalently, in this normal distribution, the probability equals the computed area in the interval ranging from minus infinity to 27.5 under the normal curve as shown in this figure. Below each figure, our solution is given. If we copy this binomial command and paste at the R console, we get the result printed at the R console. Similarly, if we copy this normal command and paste at this R console, we get the printed result here. Here we see that the result matches up to the second place of decimal. Now we shall discuss on the discrete probability for this lower tail event. That is the random variable x taking values less or equal to some specified value x. Here we are interested in approximating this probability by the area in an interval ranging from negative infinity to 0.5 more than the value x in the normal distribution. Consider this example that no more than 80 out of 300 former smokers will resume smoking within 6 months of quit. In the past, 30% did resume smoking. Here the binomial parameters are n is equal to 300 and p is equal to 0.3. And the specified value for the random variable x is 80. We shall approximate this discrete probability x less or equal to 80 using normal distribution. Since the random variable x includes 80, here in this binomial distribution, the computed sum of the discrete probabilities from negative infinity to 80 is shown in this figure. Equivalently, in this normal distribution, the probability equals to the area in the interval ranging from negative infinity to 80.5 in this figure. Below each figure, our solution is given. If we copy this binomial command and paste at this R console, we get the printed result here. Similarly, if we copy the normal command and paste at this R console, we get the next result here. Here we see that the result matches up to the second place of decimal. Next, let's discuss the open discrete probability for this upper tail event at the random variable x taking values strictly above some specified value x. This is approximated by the area in an interval ranging from 0.5 above the value of x to infinity in the normal distribution. Consider this example of more than 85 boys in a total of 150 parts with 50-50 probability for boys and girls. Here the binomial parameters are n is equal to 150 and p is equal to 0.5. Here in this problem, we are approximating the discrete probability that the random variable x lies strictly above 85. That is, this probability, which adds all the point probabilities above 85 as shown in this figure, which is approximated by the area from 85.5 to infinity in the normal distribution as shown here in this figure. Both the R solutions are given here. First, copy the binomial command and test at the R console. And we get the result printed here. Next, copy the normal command and paste at the R console here and get the result printed here. We see here the results match up to the third place of decimal. In the last example, let's discuss the closed discrete probability for this upper tail event, that the random variable x taking values greater or equal to some specified value x. This probability is approximated by the area in an interval that ranges from 0.5 below the value of x to infinity in the normal distribution. Consider this example of at least 87 out of 120 cars at the roadblock don't get the ticket. In the past, 68% do so. Here, the binomial parameters are n is equal to 120 and p is equal to 0.68. Here, this probability is the discrete probability that adds all the point probabilities above 87 as shown in this binomial distribution figure, which is approximated by the area from 86.5 to infinity in the normal distribution as shown here in this figure. Both the R solutions are given here. First, copy the binomial command and paste here at the R console and get the result printed here. Next, copy the normal command, paste at the R console here and get the result. Here we see that result match up to the third place of decimal.